I said that I was going to discuss energy, and let's quickly do this. So we have basically, let's just discuss this. We have a capacitor and an inductor. We know that both of them have some energy. So capacitor has electric energy, inductor has magnetic energy, but nevertheless, it's an energy. And somehow, since there is no resistor involved in here, the energy should be conserved. Let's check that whether that's indeed true or not, right? I'm just going to write down the energy of capacitor. So I'm just going to quickly do it in here. So the energy of the capacitor is, Q is the charge on it. So therefore, this is 1/2 of Q squared divided by C. So I'm just going to write down the expression for the charge in here. So therefore, this is Q0 squared over 2C times, I'll just write cosine squared omega t in here. I don't want to make this complicated. So therefore, the energy of the capacitor somehow is also changing periodically, but it's changing between 0 and this maximum value in here. Okay. Let's talk about this in a moment. So let's just also write down the energy of the inductor. So in that case, the formula is 1/2 of L times I squared. And when I do this, sorry, let me actually do this like that. So that's Q0 over square root of LC squared sine of omega t squared, right? When you do the calculation, then you're going to see that the coefficient in here is going to be the same. Q0 squared over 2C again. I mean, if I write it in terms of the initial charge, this is sine squared omega t. Okay, so that's the energy of the inductor. And so therefore, if I compute the total energy, that's the energy of the capacitor plus energy of the inductor, you can see that both of the trigonometric functions have the same prefactor. So it's Q squared over 2C, basically the sum of the squares of the cosine and the sine functions. And so somehow they add up to equal to 1. So therefore, the total energy is Q0 squared over 2C, which is basically the initial energy. But this is constant. The energy is conserved in here, just as we have expected. And so therefore, the total energy is equal to the initial energy. Right? I can also show it with some kind of graphs and things like that. I'm just going to do it like that. I don't think that we need to spend too much time on this. So this is the time axis. So let's say that first I draw the energy of the capacitor. So it is a trigonometric function of that form. Right? Yeah, whatever. Okay, so it just starts from some certain initial value. And it decreases at the initial moment, so it just decreases to 0, and then starts increasing again to the initial value, and then so on. It just continues like that, and so on. Okay, so what about the energy of the inductor? So let's just, I'm going to draw this with the, this thing like that. So the energy of the inductor this time changes like this. Basically, it is maximum when the capacitor energy is minimum, and it is minimum when the other one is maximum, and whatever. So that's the energy of the inductor. And finally, their sum, I'm just going to show it like that with a white color. So that's the total energy. So that's always constant. So as a result, the energies change between, well, the energy of the capacitor and the inductor change, but the total energy is constant. So that means they continuously exchange energy with each other. All right? That's basically as simple as that. In any case, let's just continue then. Continue to what? I'm just going to discuss this Um, I'm also going to do a mechanical analog in here, but let me try to discuss it in terms of the energy. So I'm just going to draw the circuit in here, probably a better circuit, a better picture. Yeah, well, so let me actually keep that this one in here, and sorry, and then I'm going to copy paste. All right, this is something that I do all the time in every year, so therefore I'm also going to do it in here too. Let me flatten all the layers, all right? So this is the initial moment at time t equals 0. Let's talk about this. This is at time t equals 0. Right? At time t equals 0, the capacitor is completely charged. So that means there are these positive charges in here plus Q0 and an exact same amount of negative charges on the other plate. And there's no current, so the current is 0. All right, but we know that these two plates are connected with a wire, and inductor is essentially a wire, so therefore a current will start flowing along that direction. Right? So eventually, at some point, some time later, we will see that there's a current flowing in here. So there's a current. Okay. And so as a result, the charge on the capacitor will decrease. Okay, but I mean, let's just continue further in here because, I mean, as long as there's a charge in here, this charge is going to discharge through the wire. And so as a result, it will keep decreasing. So eventually, we come to a point where there is no charge on the capacitor, but there is a current on the inductor, right? So that's basically at quarter period. Okay, so from the energy point of view, all of the energy was on the capacitor and none on the inductor. Because of that process, the energy is transferred continuously to the inductor. So we come to a point where the capacitor is completely empty and the inductor is now has all the energy. Okay. Now, what is interesting in here is that this situation also cannot continue forever because we now have an inductor which has a current on it. There's a current flowing on it. And we know that this current cannot suddenly change. So as a result, this current is going to keep continuing. Okay. So let me just draw an arrow in here, right? So that's an arrow. Okay. So as a result, the state is going to evolve to something else. So this current will keep continuing in this direction. Well, it will, of course, start decreasing because a current will tend to decrease if there is no EMF device. But in the meantime, it's going to start charging up the capacitor, the lower plate of the capacitor, right? So the current will start decreasing, but in the meantime, this charge is going to increase. So eventually, there comes to a point where this current becomes 0, right? Current basically decreases to the value 0, in which case the capacitor is going to be completely full, but with the opposite polarity. Okay. So as a result, in that case, we basically have the charge Q0 on the lower plate, plus Q0 on the lower plate, and minus Q0 on the upper plate, because we know that in this moment, the energy of the inductor is 0. So all of the initial energy of the capacitor should be on the capacitor. So, I mean, this and that configuration, they have the same energy, so therefore, they should have the same charge, but with opposite sign. Okay, so that's the time, which is basically half of the period. okay? And then the same argument repeats again. So we basically have a charge capacitor, and so as a result, it will start discharging. So this time it will start discharging along that direction, okay? So in any case, then the state changes to a situation like that. So we come to a point where there is a current flowing in the opposite direction now, and the amount of the charge becomes zero because of that discharging in here. Again, the same argument. So this current cannot continue forever like that. So it will decrease, but in the meantime, it will charge up the capacitor. So as a result, we come back to the initial configuration again. So as long as there is no dissipation, since there is no resistor, there is no dissipation in here. As long as there is no dissipation, the energy will continuously go back and forth between the capacitor and the inductor. There is no steady state situation in here because a capacitor, a charge capacitor is going to discharge as long as there is some kind of a connection between the plates. Also, if there is some kind of an inductor with a current on it, well, this current is going to change something. So as a result, you cannot have a situation which is static, right? So something should be changing with time. Right? So that's basically what we call as the LC oscillations. And we can have a mechanical analog in here. So I think I'm going to draw it somewhere in here. So that's the mechanical analog. Okay, so I'm just going to consider a mass attached to a spring. Okay, so let's say that this is the equilibrium position. So here, for example, you have some kind of a displacement. So that's the initial condition, for example. So initial velocity is zero, so at t equals zero. In that case, the kinetic energy is equal to zero, and the potential energy is maximum. Okay, we know that because of that, there's some kind of a force in acting on the mass. So therefore, it will start moving towards left. So eventually, therefore, the spring is going to reach to that situation in here. So that's the equilibrium position, where the mass is the object is moving towards the left, so it has a velocity, but there is no displacement in here. So that's basically the quarter period. At the quarter period, we have the kinetic energy is maximum, and the potential energy is equal to zero. But this is a situation which cannot stay there because the particle is already moving, right? So basically, this is a conversion of the potential energy to kinetic energy. But this kinetic energy will basically be converted back into the potential energy again. But this time, it is in this form. So in that case, the spring will get compressed. So that's the equilibrium orientation. So there is a displacement now. It is minus x0. Yeah, whatever. So the displacement is along that direction. So I would call this as minus x0. So that's basically half of the period. In which case the kinetic energy is zero again, and the potential energy is maximum. And then, well, the same thing repeats again. So this is again pushed back to the equilibrium position. Again, the velocity is like that. So this is at time t equals 3/4 period. In here, the kinetic energy is maximum again, and the kinetic energy is maximum, and potential energy is equal to zero. So we basically have some kind of a periodic exchange of energy between the kinetic energy and the potential energy, all right? So this is what we call as a mechanical oscillator. Sorry. This is a mechanical oscillator. Where the total energy is basically the kinetic energy plus the potential energy is constant. We cannot have a situation where there is a kinetic energy, but it doesn't change. There is a potential energy, but it doesn't change because of the nature. So if there's a kinetic energy, it means that the particle is moving, so something is changing. If there's a potential energy, we know that there is a restoring force, so therefore the position will change. So as a result, the total energy doesn't disappear. It basically periodically changes between the kinetic form and the potential form, all right? So as a result, we have some kind of a periodic motion in here. This is exactly the same in the situation in here, but this time, I mean, it's not a mechanical thing. So the energy is exchanged between the capacitor form and then inductor form. You can think of it as the electric energy and magnetic energy, right? So let me also write down the time in here. So that's 3/4 of the period. Okay, so again, we have a situation in here. So if the capacitor has an energy, it cannot stay there forever. Somehow the capacitor should discharge. If the inductor has an energy, so that means there's a current. Again, the energy cannot stay there forever. So the current is going to change. So therefore, the energy of the inductor is going to change, right? There's a perfect analog between these two situations, the LC oscillations and the mechanical oscillations. There are basically two kinds of energy, and it's basically completely, it's periodically exchanged. The energy is periodically exchanged between these two forms. Yeah, let's just come back to the stupid question like that I have asked, whether this is the electromagnetic energy, whether it's a kinetic energy or the potential energy. This is a stupid, well, it's a stupid question, right? Yeah, I think that there are some deeper things in here. I don't know what the answer should be to that question. But if you make an analog in here, it looks like something like, I mean, the energy of the inductor should be thought as the kinetic energy in here because it is associated with something that says that something is changing, right? Something is moving in here. Because if the inductor has an energy, there's a current in here, and so therefore the charge carriers are moving. So you might think of it like this. That's okay. But just keep in mind that it's not the energy of the charge carriers, right? It's the energy inside the magnetic field. The charge carriers do not actually, they have their energy themselves, but the energy of the inductor is not the energy of the charge carriers, right? But somehow it is associated with this current thing in here. In any case, let me kind of answer this question, whether we should count this as the kinetic energy or this one as. In some cases, if you make these kind of analogies, some people actually treat the inductor as the kinetic energy and this as the potential energy. But it appears that the other approach is also kind of useful. So you can treat the capacitor as the kinetic energy, capacitor's energy as the kinetic energy. And this one is the potential energy. I know that there are these kind of treatments. So as a result, it's just an interpretation, right? So as a result, I mean, there's no meaning to the statement that, well, this is kinetic energy and that's potential energy. It's actually meaningless because you can look at it in different ways. Somehow you always get the same result. I would think of it like this, actually. But in any case, it's basically the energy of the electromagnetic field. And it doesn't matter which one you think that it is kinetic, which one is potential. It's just words, actually. In reality, there's this physical entity that we call as the electromagnetic field, and it has energy. That's it. I don't have to. I don't have to associate with that energy with a certain kind of energy, right? And that's basically what I think. So, as a result, for me, this is just energy, right? I know that it's an energy, so that's something that's undisputed. And so as a result, we have to use basically the undisputed concepts entirely. But if you want to make some analogies, of course, you can say that this is similar to kinetic energy and that's similar to potential energy or something like that. Okay. So the question is, what if there is a resistor in the circuit? Let me say this, by the way. There's actually a lot of things going on about these quantum computers and things like that. I think there's actually a big fuss about it. Well, I'm also working on this field as well. In any case, it is possible to produce these kind of circuits with zero resistance, right? These are called the superconducting oscillators. It appears that it's not quite easy to actually build capacitors and inductors from superconductors in the conventional way, because somehow you have to deposit these superconducting things on some surfaces and things like that. But I mean, because of the fact that every circuit has an inductance, and if there are like two conductors which are nearby, they somehow act like capacitors. You can actually construct some from superconductors an LC circuit like that. So the modern qubits that, for example, IBM is using, right? It's not just IBM. I mean, lots of companies are actually producing these superconducting qubits. They're actually based on these kind of oscillators, right? But at your level, of course, it's hard to understand why this kind of an oscillator has some relevance to quantum computation. I'm not going to go into this because there are some kind of technical and physical details in there. But this is essentially what they are producing there. It's an LC oscillator in there. And there's no resistor, because somehow, if you want to start oscillating this thing, you want them to continue forever. Because if there's a resistance, then of course the energy will get lost and somehow this oscillation will die down. But they don't want it, so that's why they are building this thing out of superconducting. So as a result, I mean, this LC oscillator thing is not an entirely imaginary thing. And in reality, we can construct these kind of things, no problem. But we have to use superconductors, so as a result, these are like at temperatures, let's say, this is an absolute temperature. This is like about 1 millikelvin. We haven't talked about temperatures, actually, but 0 Kelvin corresponds to minus 273 point something degrees centigrade. This is above this absolute zero. Well, all temperatures should be above the absolute zero, but it's not even 1 degree above. It's about 1 millikelvin above the absolute zero. So somehow you have to cool these to very low temperatures to be able to do these kind of quantum computers, actually. But in any case, that's something else, right? Okay, so let's see what happens if there's a resistor. So it's the same thing in here, right? It's the same problem. I just add a resistor in here and an inductor. Okay, so let's say it like this. This is the situation in here, and this is the inductor. So at time t equals 0, the switch S is suddenly closed. Okay, so the question is, what happens next? All right. And the answer is simple if you just look at it from the energy point of view. So I'm not going to write down the equations for the circuit and things like that in here. We can write down, there's no problem with writing down the equations. but the solutions are complicated. Um, I think when you take physics 209, you will be able to solve these kind of equations. They are also simple equations, but analysis becomes a little bit difficult. But I'm just going to explain what happens in here. What's important in here is that this resistor now converts energy into heat. And so as a result, we are going to have what we call as damped oscillation. All right? It's just an oscillator, like the mechanical oscillator, with friction, with air friction, let's say. There are situations where, like whether this damping is weak or not, whether this resistance value is a small value or not. If it is small, it's just a weak damping, in which case you basically see some kind of a decrease in the amplitude of the oscillations, right? I'm just going to do it like that. So let's say that I'm just plotting the charge as a function of time. So that's what you're going to see. So there will be some kind of an exponential damping of the oscillations. Right? Eventually, of course, it will die down, but the exponential somehow, I mean, the amplitude dies down exponentially. So let's say it like this: amplitude is like is about like e to the minus t divided by some time constant or something like that. Okay, so that's basically what the effect is, and that's the only thing that we should keep in mind. All right, you don't have to learn anything else, but there are some other details in here, like the period in here also changes because of the damping. And so as a result, if the damping is large, this period becomes, I think, so long that you don't actually see any oscillations. This is basically what we call as an overdamped situation. I mean, so the damping is so great that the energy loss is so great that this thing actually doesn't have time to oscillate. And that's what we call as overdamping or whatever. It's basically a detail that I don't want to talk about. But in any case, we basically have this kind of situation. So only a qualitative understanding of this is basically is necessary. Okay, so as a result, I mean, in all of these high temperature, ordinary conductor circuits, we always have a resistor, right? It's not a superconductor. So we always have a resistor, so therefore we have these kind of oscillations. So what people would like to do is, I mean, if they want to produce these LC oscillations, they want to keep this resistance to be as small as possible so that you can kind of see a lot of oscillations actually. So the number of oscillations that you can see in a significant amount of time is kind of what people call as the quality factor. But I think I'm not going to go into these kind of things in here. Okay. So we are not done with these kind of circuits. So what happens if I put an EMF device in here? I'm not going to go into this either, but I'm going to talk about the AC circuits. All right, that's one of the unfortunate things about this chapter in here. There are too many things in there, too many topics from different fields. So as a result, the AC circuits are somehow placed in here because somehow an inductor in an AC circuit behaves in a certain way. A capacitor also placed in an AC circuit behaves in a certain way. So, I mean, these devices, a capacitor and an inductor in alternating current circuits, they also fulfill some functions. And this is a little bit different than their functions in RC circuits or LR circuits. And so as a result, as a topic, we have to investigate this thing in here. But I don't want to do any electronics in here. So as a result, I'm just going to give some essentials in here, right? And as a result, I'm not going to go some of the details. But I mean, there will be a lot of information in here. So in any case, we basically have in these kind of circuits some kind of an AC EMF device. We usually show it like this. So that's AC EMF device. And then on a circuit, we might have a resistor, a capacitor, and an inductor. All of them behave in a certain way. So initially, of course, I'm just going to look at the resistor basically, and then I'm going to add all of these. Of course, it doesn't have to be like that. I mean, there might be some other branches in here with some certain inductors and resistors as well too, right? So I don't have to have everything on a single branch like that. And I might even have some additional EMF devices in here with the same frequency perhaps, okay? So this is the complicated circuit. So we are not going to look at these complicated circuits. I'm just going to look at some simple circuits. The most complicated circuit will be the series RCL circuit, right? Or LRC, series LRC circuit. But in any case, I'm just going to start slowly. So I'm going to start with the AC EMF device. Okay. AC EMF device. Okay. I think in the case of induction topic, I have talked about this. I was talking about this kind of a circuit where I mean, some kind of a wire frame, if I rotate it inside a magnetic field with constant angular velocity, in that case, we have said that the EMF produced would be like, at time t would be like epsilon 0 times cosine omega t plus something like that, right? I mean, remember this example because this is how people produce the alternating EMF, alternating current in power plants. There's actually a constant magnetic field in here, and somehow some kind of an energy is used to rotate this wire frame inside this magnetic field. And as a result, somehow this energy is converted into electric energy. And somehow this charge carriers carry this energy to whatever, some other parts of the circuit, right? In any case, I mean, there is a way to produce them, and induction is the best way to produce them, right? There are some alternative ways as well. So there are these transformers and things like that, whatever, but I don't want to go into these. The symbol is this, basically. So that's the AC EMF device. And this corresponds to an EMF where the EMF has this expression in here. So that's epsilon 0 cosine omega t plus phi. It's in this form in general, and it has some kind of a time dependence like that. So as a result, the EMF has this kind of a time dependence. It's a periodic time dependence. What's important in here is that the EMF is positive from time to time along this given direction, and sometimes it is negative. So as a result, at this point, we get used to the fact that the EMF can be negative from time to time, okay? Because it's time dependent, but we always choose some kind of a direction. So let me write it in here with small letters. So that's the direction to express the EMF as a function of time, right? So when we say that at this moment the EMF is positive, it is with respect to that arrow, right? And if I have chosen the opposite arrow, I would describe the same physics with a negative value of the EMF. Okay, so I'm using this sign convention in here. So there's always some kind of a direction that I choose to express that EMF value. Okay, here, epsilon 0, sorry. This is E0, right? This E0 is the maximum value of the EMF, and it's also the minimum. Minus E0 is the minimum. So this E0 is called the amplitude. Of EMF. The unit is, of course, volts, obviously. Phi in here is called the phase, or sometimes phase angle. Let's just say that depends on when time started, all right? I mean, we express the time starting from some initial time. By choosing that initial time, we can choose that phase angle to be equal to 0, for example. So I'm going to always do this, but sometimes I'm going to choose this phase angle to be 0 on the EMF. Sometimes I'm going to choose it on the to be 0 on the current, right? I think, yeah, whatever. I mean, in general, depending on when you start the time, there might be a phase angle in here. This function might be a cosine or sine. It doesn't matter because a cosine can be expressed as a sine by changing the phase angle, actually, by just shifting the phase angle by 90 degrees, I believe. So it's just a simple change. So as a result, it's not something serious. This part is not serious, all right? But it's either sine or cosine. Okay? Omega is called the angular frequency. Why angular frequency? Because it's a number that appears inside the argument of the cosine. So the argument of the cosine should be in radians, right? And so as a result, when I multiply the time with that constant, the result should be an angle, and that's why we need to have angular frequency in here. Okay. This is also the same as the angular velocity of the wire frame that is rotated to produce this thing. Okay. And this is one of the reasons why we sometimes, I sometimes use angular frequency and angular velocity terms interchangeably, because the meaning is blurry in a way. So you don't usually, I don't usually distinguish angular frequency and angular velocity from each other, but strictly from this AC circuit point of view, this is just the frequency. Okay. We say omega is 2 pi f, where f is the frequency. Okay. We know that f is equal to 50 hertz. It's about 50 hertz in mains electricity. In the electricity that we use, in the electricity that everybody uses, all right? This frequency is about 50 hertz, or sometimes I think in some countries it's 60 hertz. And there's a special reason why this is chosen like that, but yeah, I forgot what the reason is. But in any case, this is some kind of a design. But once this is chosen, it has to be 50 hertz for all kinds of circuits, because, I mean, somehow they have to be, all of these power plants and the electric infrastructure, they have to be consistent with this frequency. Otherwise, there would be a very undesirable things that's happening if there's some kind of a mismatch in frequencies. Okay, so that's important. What else in there? Well, nothing else. Okay. So we have the LR, the the R circuit, right, we have an AC EMF device connected to a resistor. And in that case, we can see what's happening in here. There's going to be a current in here. I'm going to use this direction to also measure the EMF as well, right? It's the same. I'm going to use the same direction to measure both the EMF and the current. Let me show it like that. So as a result, if the EMF is in this form, epsilon 0 times cosine omega t plus phi, the current in the circuit would be the EMF divided by R. So therefore, this is epsilon 0 over R times cosine omega t plus phi. Okay. So here, this epsilon 0 over R, sometimes I just write this thing down as I0. This is cosine omega t plus phi. So I0 is the current amplitude. I mean, just think of it as maximum current, right? The maximum value of the current. We can think of it like that. And it says that the maximum current in this kind of a circuit is equal to the maximum EMF divided by the resistance. It's just the usual Ohm's law. Right? There's nothing complicated in here. Unfortunately, nobody uses this expression. Nobody uses the amplitude, so they use something called the an RMS value. But let me introduce this. I don't have much time, so as a result, I'm going to start from here tomorrow. But let's talk about the power of energy dissipated. Power of energy dissipated on the resistor. On the resistor. This is basically the instantaneous power. It is I squared times R. So therefore, this is I0 squared times R times cosine squared omega t plus phi. So this is basically instantaneous power. And you can see that the amount of the energy dissipated depends on time. So as a result, at some certain times, this is 0. At certain times, it's maximum. So the power is not constant. And we don't like the energy consumption, which is not constant. So as a result, we would like to replace this with a constant value. And I'm going to explain how we do this, right? Let me postpone this tomorrow. So by using this, people then say that, well, instead of the amplitude, we use, let's use something else to express the amount of the current in the AC circuits, right? So I'll also talk about this tomorrow. All right, so let me stop the recording.